Hello everyone. Sorry I couldn't be there today. I'm going to the practice exam B. And so let's look at the very first problem here. It says provide IUPAC names for the following molecules. And so I have to look at the two substituents, make sure there's not a common name that I can call either one of them. So I have a nitrogroup and an ethyl. Look at the relationship between the two, so they're right next to one another, so that makes it ortho. Okay, ethyl and nitro. Ethyl's first alphabetically, so it'd be first in the name. So ortho-ethyl nitrobenzene. If I look at the next one, there's an OH attached to a benzene ring, so that one does have a common name. So that'd be a phenol, the OH attached to the benzene ring. I have a chlorine attached to it. It's 1,3 to one another, so that's meta. So I got meta chlorophenol. Look at the next one. So circle any of the following compounds that can be classified as aromatic. And so I've looked at the first one. It's considered conjugated because I got some heteroatoms there with a lone pair of electrons. And when you have oxygen, remember 2 lone pairs of electrons, and so one of those lone pairs is up in the pi system. And I have 2 of them. So that's 4 electrons computed by oxygen in the pi system. So completely conjugated, I have 1, 2, 3, 4, 5, 6, 7, 8 pi electrons. So remember the Huckel values are 4n plus 2. This has 4n pi electrons, because 8 pi electrons. So that would be anti-aromatic. This one's cyclic, conjugated, but again, remember each double bond, 2 pi electrons. So 4 pi electrons, again, not a Huckel value, so anti-aromatic. But look at this one, double, single, single, but I have a charge. Remember, if you have a charge, you can tolerate just skipping the conjugated sequence. Cyclic, planar, 2 pi electrons, because the positive charge, you count minus charges as 2 pi electrons. Positive charge do not contribute any electrons. So that is a Huckel value, 2 pi electrons. 4n plus 2, if you plug in 0, you get 2 pi electrons. Look at the next one. Again, it's conjugated, cyclic, 1, 2, 3, 4, 5, 6, 7, 8. 8 pi electrons, not Huckel value, so anti-aromatic on that one. Next problem, which combination of diene and dienophile is needed to prepare the following compound? So I want to locate what was my diene. And so you know you always form a cyclohexene ring, and the double bond goes between 2 and 3. Now, I chose this double bond over here because that way I can make my dienophile over here, because remember I have to have electron withdrawing groups attached to my dienophile. So this is my 5 and 6 of my 6-membered ring that's formed. So I'm breaking that back apart. Remember, you always have your diene and then your dienophile. Okay, so if I go back here, between 1 and 4, I have a 2-carbon bridge. So between 1 and 4, I make a 2-carbon bridge. So that would be my diene for the reaction. Now between 5 and 6, I have CO2, CH3s attached to both sides. And I have a double bond still here. Remember when you normally add, you end up with a single bond. So if you still have a double bond there, that means your starting dienophile was a triple bond. So I can then add my CO2, CH3s. Normally we show stereochemistry, but triple bonds, linear compounds, linear. And so I don't show same or opposite sides only if you have a double bond there. So there's my diene dienophile. Next one. Using curved arrows to indicate electron flow, propose a mechanism for the following nucleophilic aromatic substitution reaction. So I'm given that's a nucleophilic aromatic substitution. So my nucleophile will be my methoxide ion. So it's going to substitute on in place of the halogen attached to the ring. I have an electron withdrawing group at the ortho position, so this reaction would work. So the mechanism, it adds to your carbon with your halogen with your leaving group, puts the electrons into the ring, so that's my Meisenheimer complex. Stabilized through resonance. I could move the minus charge on down into the ring, or I can move up here with the carbonyl, stabilize it that way. So that's my Meisenheimer complex. Then to get my final product, those electrons reform the double bond, so I regain my aromaticity there. Kick off the leaving group. Get the product. Next one, outline a synthesis of the following compounds starting from benzene. I'll start from benzene. Look at the two things I add. I have an alkyl group here, and I have a chlorine. Both of these are orthoparadirectors. I want this substitution to take place in meta. So I need a meta director on there. And so what I could do is instead of Friedel-Crafts alkylation, I could do an acylation. So if I do an acylation and have the double bond here, the double bond O, that'd make it a meta director. So that's what I'm going to do. So I have C6H5, which is benzene, CH2, and C double bond OCl. Okay. So I'm going to add the two carbons in the benzene ring to it. Now I've got my meta director on there. I can go ahead and add my chlorine. Okay. So the chlorine, the carbonyl electron withdrawing group, so it directs to the meta position. So now I have just an alkyl, just a CH2 here, and now I can add hydrogen. Remember, carbonyls are adjacent to a benzene ring. The benzene activates them, or they're susceptible to hydrogenation, so you can get rid of your carbonyl basically. So it converts it to your CH2, reduces it all the way to the CH2. Let's look at this next one. It says, draw a segment of the polymer that might be prepared from 2-phenyl-1,3-butadiene. So I'm first going to draw my starting material. So bute is 4 carbons, diene, 1 at the 1 and 3 positions. So 1, 2, 3, 4. So there's 1,3-butadiene, 2-phenyl. So I'm just going to put pH to stand for phenyl, but that's a benzene ring if you want to draw out the benzene ring. Now, I want to show a 1,4 addition mechanism for the polymer. So I'm going to draw the same thing. Without the double bonds there. So I'm going to extend away from the 1 and 4 positions. Put those atoms in brackets, so I still have 4 carbons in my chain there. Remember, for 1,4 addition, you see addition take place at 1 and at 4, and your double bond moves between 2 and 3. Double bond between 2 and 3. So that'd be the segment of the polymer that you can compare from that. You could also do 1,2 addition if you want to, and I still count it right, but what we're looking at now is the 1,4 addition products. So let's look at the reaction page. So draw the principal organic products for the following reactions. Be sure to indicate stereochemistry where appropriate. I've got 2 different things on the ring here. So nitro is a meta director, so direct to the meta positions. Methyl is alkyl group, so alkyl groups are orthopara directors. The para position is blocked. So this is an example where the directing effects reinforce one another, so that's where your substitution will take place. Next one, have a nitrile group, multiple bond there, so electron drawing group, so meta director, so this meta position is blocked, so I'm going to asterisk there, so it directs the meta position. OCH3, lone pair of electrons, strongly activating, directs orthopara. So in here, the directing effects oppose one another. And in that case, you go by the one that's the more powerful activator. Or if you're going to have strongly deactivating, you're going to have strongly activating. So this one will be the one that will have the dominant influence. Rarely see substitution take place in between the 2. So that means you'll see substitution here and here. So 2 major products there. Look, the next ones, next few here. So this first one, I have a Diels-Alder reaction. Okay, so I recognize I have a conjugated diene and a dienophile, something a double bond with 2, in this case 2 electron drawing group. I just need 1 electron drawing group. So I know Diels-Alder always forms that cyclohexene ring. Okay, so I see what else is attached. Well, this doesn't have anything attached to it, so I'm okay there. 5 has a nitrile, 6 has a nitrile, so I need to show those attached. Stereochemistry is maintained, so here they're on the same side. On your ring, they need to be on the same side. Okay. So I do them both going up there. They could also be both going down. Both are equally likely, so you get a racemic mixture of those 2. So I could flip this over, it'd be the mirror image, so those are enantiomers. Next one here, so again, locate my diene. Here's my dienophile. Draw my cyclohexene ring that's formed. So between 2 and 3, I have a 2 carbon bridge. So between 2 and 3, 2 carbon bridge. Between 5 and 6 I have the 3 atom bridge there, the oxygen in it. So you'd also stereochemistry going to show the hydrogens going up or down in that case. But I'd be mainly looking on that one to see, just knew how to connect them all together. So here I have DBr reacting with the conjugated diene. So remember, D is deuterium, so it reacts just like hydrogen, but I can tell it apart between other hydrogens. So it's isotopically labeled, basically hydrogen. So as a proton and a neutron there for that hydrogen. So I want you to show the 1,2 addition product and the 1,4 addition product. So 1,2 addition. Your deuterium would add first, so it's going to create the positive charge in the position next to your double bonds. That's where your bromine adds. Then my 1,4 addition. So deuterium adds to 1, double bond moves between 2 and 3, bromine adds to 4. Remember, that comes from the carbocation intermediate here. Positive charge, form a resonance structure. Move this double bond over, creates a positive charge at that position. So there's the 2 possible products, and you can actually draw more. Here you have a chiral center, so you could draw the bromine going up or down in that case. No chiral center there, so just the 1 product. Let's look at the next one. What is the major monosubstitution product from the Friedel-Crafts reaction of benzene with 1,chloro,2-methylpropane in the presence of aluminum chloride? So propane, 3 carbons, 1,chloro,2-methyl. So this is Friedel-Crafts. If I look at the electrophile for this reaction, okay, forms a complex of aluminum chloride. This is a positive charge on that carbon where the chlorine's attached. The adjacent position is more substituted. So since the adjacent position is more substituted, you'll see a hydride shift. That hydrogen will shift over. You create this more stable carbocation. So that's your electrophile for the reaction. So that is what your benzene will add to. So you get tert-butylbenzene there. Next one was I think a nickel problem to the other one we worked in class. And so I do Friedel-Crafts acylation. Add the C double bond OCH3. You get rid of the carbonyl, so I'm going to just use a hydrogenation there. Then I need to add a bromine to the pair positions. This is ortho-pair director. So just electrophilic aromatic substitution at the bromine. You don't want to add the bromine to the allylic position. That's NBS. Then I'm forming a double bond, secondary halide. So E2 elimination is you use a strong base. So we'll do sodium methoxide. Any strong base will work there. My battery's getting low on my laptop, so I'm going to skip to the multiple choice, but if my laptop's not dead by then, I'll come back to that bonus question. So which of the following compounds is a double bond that's conjugated with the pi system of the benzene ring? So I need to draw all these out. So para-ethyl toluene. So that does not have a double bond conjugated with a benzene ring. 2-phenyl 1-decene. So decene is 10 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2-phenyl. One decene. Okay, so that one does have a pi bond that's in conjugation with the benzene ring. So 2-phenyl 1-decene is your correct answer. If you look at the next one, 3-phenyl cyclohexene. So it goes double, single, single, double. So that's not in conjugation. And 3-phenyl 1,4-pendiene. So there's your pent. 3-phenyl 1, 2, 3, 4. Again, you have double, single, single, double. So not conjugated. So B, correct answer. All the following groups are activating orthopair directors when attached to a benzene ring except orthopair director, so lone pair of electrons, activator, so orthopair directing. Nitrogen, lone pair of electrons, activator. CH2CH3 alkyl group, activator, orthopair directing. Here, C double bond O, electron withdrawing, deactivator, and also meta director. So B, correct answer there. Rank the following in terms of increasing reactivity towards nitration. So I just want to go most reactive here. So I'll look at the activating effects. So oxygen, OH group, strongly activating. CO2H, that double bond, C double bond O, strongly deactivating. Halogens are weakly deactivating. So it says least to most. So my least reactive would be one with the deactivator, so C. And then the weakly deactivating would be D. Okay. Then I'd go to A, then my most reactive would be my OH group. So D, correct answer. Best method to convert nitrobenzene into aniline. That's a tin chloride. You use to convert your NO2 into your NH2. What would be the major elimination product? So if you look at your possibilities here, here's your double bond. So here's your halogen. So you form your double bond here or here. Okay, 2 possibilities. But you want to look and see which one's more stable. Okay, they're both equally substituted. But if you put your double bond here, it's in conjugation with the ring. But the double bond here, not conjugated. So conjugation adds stability. So that will be your major product there. So not equal amounts. Which of the listed compounds is not an effective substrate for the process shown? So I will make 2 CO2H. So remember, for this reaction to take place, you need benzylic hydrogens. So this has a benzylic hydrogen, 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 no benzylic hydrogen there. So even though you might think the answer would have been this one, because it looks different than the other ones, you still have benzylic hydrogens there, and so it would still oxidize at those positions. So A is your correct answer. Major product for the following reaction. So you want to know which ring it takes place on. So this is weakly activating. Halogen is weakly deactivating. So this ring will be activated. There's something already at the pair position, so it's going to direct ortho. I'm adding a nitro group. So ortho position on this ring. B, correct answer. Which of the following compounds undergoes bromination of its aromatic ring at the fastest rate? So the one with the lone pair of electrons right adjacent to the ring, so it can donate electrons and have that resonance effect of the ring, is going to be the one that reacts the fastest. Okay, so here's alkyl group, weakly activating alkyl group, weakly activating carbonyl, it's deactivating. The one with the lone pair adjacent, directly adjacent to the ring, will have the strongest activating effect. So it'll react the fastest. B, correct answer. For the following reaction, the major products are shown. So here, this is 1, 2, so there's the 1, 2, here's my 1, 4 addition. So these provide an example of, so here's a low temperature and a higher temperature. So that's kinetic control at low temperature and thermodynamic control at high temperature. Okay, so A, correct answer. Choose the best reactions for the following reaction. So if I just look at each of these, so I'm adding, well this, if I start off with the chlorobenzene and I do it for Delcraft's acylation, this isn't worth a pair directly, so that wouldn't work. Now here I have 2 benzene rings, and chlorination, that is a meta director, because there's a carbonyl there, so it's directing to the meta position, so it could add the chlorine there. So that wouldn't work. That wouldn't work. That's not adding anything to the chlorine. And so this one would work. So B, correct answer. So I'm at 5% battery now. I think I'll just probably try to email you about this one. I don't want to, I forgot to bring my charger today. So I'm going to stop the review there, and then I'm going to try to do another recording if I have enough power for this bonus problem. I'm going to stop this one for now.